objects. Class decimal dot decimal, value is equal to 0, context is equal to none. Construct a new decimal object based from value. Value can be integer, string, tuple, float, or another decimal object. If no value is given, returns decimal 0. If value is a string, it should conform to the decimal numeric string syntax after leading and trailing white space characters, as well as underscore throughout are removed. Sign, plus, minus, digit. These are digits. Indicator, small capital E, digits. Digit, digit, dot dot dot. Decimal part, digits, dot digits, or dot digits. Exponent part, indicator, sign, digits. Infinity, infinity, INF. NaN digits, SNAN digits. Numeric value, decimal part, exponent part, infinity. Numeric string, sign, numeric value, sign, NaN. Other Unicode decimal digits are also permitted where digit appears above. These include decimal digits from various other alphabets, for example Arabic, Indic, and Devanagari digits, along with the full width digits \UFF10 through U\UFF19. If value is a tuple, it should have three components: a sign 0 for positive or 1 for negative, a tuple of digits, and an integer exponent. For example, decimal 0, 1414 minus 3 returns decimal 1.414. If value is float, the binary floating point value is losslessly converted to its exact decimal equivalent. This conversion can often require 53 or more digits of precision. For example, decimal float 1.1 converts decimal 1.1000. The context precision does not affect how many digits are stored. That is determined exclusively by the number of digits in value. For example, decimal 3.00000 records all 5 zeros even if the context precision is only 3. The purpose of the context argument is determining what to do if value is a malformed string. If the context traps invalid operation, an exception is raised. Otherwise, the constructor returns a new decimal with the value of NaN. Once constructed, decimal objects are immutable. Decimal floating point objects share many properties with the other built-in numeric types such as float and integer. All of the usual math operations and special methods apply. Likewise, decimal objects can be copied, pickled, printed, used as dictionary keys, used as set elements, compared, sorted, and coerced to another type such as float or integer. There are some small differences between arithmetic on decimal objects and arithmetic on integers and floats. When the remainder operator percentage is applied to decimal objects, the sign of the result is the sign of the dividend rather than the sign of the divisor. -7 mod 4. Example 6. Print -7 mod 4. Output is equal to 1. Decimal -7 mod 4. -3. The integer division operator // behaves analogously, returning the integer part of the true quotient, truncating towards 0 rather than its floor. so as to preserve the usual identity x is equal to x mod y into y plus x mod y remainder minus 7 divided 4 print division minus the module the mode and remainder and integer divisor operators implement the remainder and divide integer operations respectively as described in the specification. Decimal objects cannot generally be combined with floats or instances of fractions. Fraction in arithmetic operations. An attempt to add a decimal to a float, for example, will raise type error. Okay. However, it is possible to use Python's comparison operator to compare a decimal instance x with another number y. This avoids confusing results when doing equality comparisons between numbers of different types. In addition to standard numeric properties, decimal floating point objects also have a number of specialized methods. Adjusted. Return the adjusted exponent after shifting out the coefficient's rightmost digits until only the leading digit remains. Decimal 321e plus 5 dot adjusted returns 7 used for determining the position of the most significant digit with respect to the decimal point as underscore integer underscore ratio. Return a pair ND of integers that represent the given decimal instance as a fraction in the lowest terms and with a positive denominator. Decimal class methods. Print decimal. As tuple, return a named tuple representation of the number decimal tuple sign digits exponent. Canonical, Return the canonical encoding of the argument. Currently, the encoding of a decimal instance is always canonical, so this operation returns its argument unchanged. Compare. Other comma context is equal to none. Compare the values of two decimal instances. Compare returns a decimal instance, and if either operand is a NaN, then the result is NaN. Print. A is equal to decimal 4.5. B is equal to 4.5. NaN. Okay. Compare signal. Other context is equal to none. This operation is identical to the compare method except that all NaN signal. That is, if neither operand is signaling NaN, then any equivalent NaN operand is treated as though it were a signaling NaN. Compare total. Other comma context is equal to none. Compare two operands using their abstract representation rather than their numeric value. Similar to the compare method, but the result gives a total ordering on decimal instances. two decimal instances with the same numeric value but different representations compare unequal in this sort ordering. Decimal 12.0 dot compare total decimal 12. Print decimal 12 and compare total. Quiet and signaling NaNs are also included in the total ordering. The result of this function is decimal 0 if both operands have the same representation, decimal -1 if the first operand is lower in the total order than the second, and decimal 1 if the first operand is higher in the total order than the second operand. See the specification for details of the total order. This operation is unaffected by context and is quiet. No flags are changed and no rounding is performed. As an exception, the C version may raise invalid operation if the second operand cannot be converted exactly. Compare total mag. Other context is equal to none. Compare two operands using their abstract representation rather than their value as in compare total, but ignoring the sign of each operand. X dot compare total mag y is equivalent to x dot copy underscore abs dot compare total y dot copy abs. This operation is unaffected by the context and is quiet. No flags are changed and no rounding is performed. As an exception, the C version may raise invalid operation if the second operand cannot be converted exactly. Conjugate just returns self. This method is only to comply with the decimal specification. Copy underscore abs return the absolute value of the argument. This operation is unaffected by the context and is quiet. No flags are changed and no rounding is performed. Copy underscore negate return the negation of the argument. This operation is unaffected by the context and is quiet. No flags are changed and no rounding is performed. Copy underscore sign other context is equal to none. Return a copy of first operand with the sign set to be the same as the sign of the second operand. For example, decimal 2.3 dot copy sign decimal -1.5 -2.3. This operation is unaffected by context and is quiet. No flags are changed and no rounding is performed. As an exception, the C version may raise invalid operation if the second operand cannot be converted exactly. Exp context is equal to none. Return the value of natural exponential function e power x at the given number. The result is correctly rounded using the round half even rounding mode. Decimal 1.exp decimal 321.exp. Run. Class method from float f. Alternative constructor that only accepts instances of float or integer. Note: decimal dot from float 0.1 is not the same as decimal 0.1 since 0.1 is not exactly representable in binary floating point. The value is stored as the nearest representable value, which is 0 into 1.9999 AP minus 4. That equivalent value is in decimal like this. From Python 3.2 onwards, a decimal instance can also be constructed directly from a float. Decimal dot from float 0.1. This print, then decimal dot from float float NaN, then decimal dot from float float INF, then decimal dot from float minus INF. FMA, other third context is equal to none. Fused multiply add. Fused multiply add return self into other plus third with no rounding of the intermediate product self uh, product other. Decimal 2 point FMA 35. 11 is canonical. Return true if the argument is canonical and false otherwise. Currently, a decimal instance is always canonical, so this operation always returns true. Is finite. Return true if the argument is finite number and false if the argument is an infinity or an NaN. Is infinite. Return true if the argument is either positive or negative infinity and false otherwise. Is NaN. Return true if the argument is a quiet or signaling NaN and false otherwise. Is normal. Context is equal to none. Return true if the argument is a normal finite number. Return false if the argument is 0, subnormal, infinite or NaN. Is QNaN. Return true if the argument is a quiet NaN and false otherwise. Is signed. Return true if the argument has a negative sign and false otherwise. Note that zeros and NaNs can both carry signs. Is SNN. Return true if the argument is signaling NaN and false otherwise. Is subnormal. Context is equal to none. Return true if the argument is subnormal and false otherwise. Is 0. Return true if the argument is a positive or negative 0 and false otherwise. ln. Context is equal to none. Return the natural base e logarithm of the operand. The result is correctly rounded using the round half even rounding mode. Log 10. Context is equal to none. Return the base 10 logarithm of the operand. The result is correctly rounded using the round half even rounding mode. Log b. Context is equal to none. For a non-zero number, return the adjusted exponent of its operand as a decimal instance. If the operand is a 0, then decimal minus infinity is returned and the division by 0 flag is raised. If the operand is an infinity, then decimal infinity is returned. Logical AND. Other. Context is equal to none. Logical AND is a logical operation which takes two logical operands. See logical operands. The result is the digit-wise AND of the two operands. Digit-wise AND of the two operands. Logical invert. Context is equal to none. Logical invert is a logical operation. The result is the digit-wise inversion of the operand. Logical OR. Other. Context is equal to none. Logical OR is the logical operation which takes two logical operands. The result is the digit-wise OR of the two operands. Logical XOR. Other. Context is equal to none. Logical XOR is a logical operation which takes two logical operands. The result is the digit-wise exclusive OR of the two operands. Max. Other. Context is equal to none. Like max self other, except that the context rounding rule is applied before returning and that NaN values are either signaled or ignored, depending on the context and whether they are signaling or quiet. Max underscore mag. Other. Context is equal to none. Similar to max method, but the comparison is done using the absolute values of the operands. Mean. Other. Context is equal to none. Like mean self other, except that the context rounding rule is applied before returning and that NaN values are either signaled or ignored, depending on the context and whether they are signaling or quiet. Mean underscore mag. Other. Context is equal to none. Similar to mean method, but the comparison is done using the absolute values of the operand. Next. Underscore minus. Context is equal to none. Return the largest number representable in the given context or in the current thread's context if no context is given, that is smaller than the given operand. Next. Plus. Context is equal to none. Return the smallest number representable in the given context or in the current thread's context if no context is given, that is larger than the given operand. Next. Toward. Other. Context is equal to none. If the two operands are unequal, Return the number closest to the first operand in the direction of the second operand. If both operands are numerically equal, return a copy of the first operand with the sign set to be the same as the sign of the second operand. Normalize context is equal to none. Used for producing canonical values of an equivalence class within either the current context or the specified context. This has the same semantics as the unary plus operation, except that if the final result is finite, it is reduced to its simplest form, with all trailing zeros removed and its sign preserved. That is, while the coefficient is non-zero and a multiple of 10, the coefficient is divided by 10 and the exponent is incremented by 1. Otherwise, the coefficient is 0, the exponent is set to 0. In all cases, the sign is unchanged. For example, decimal 32.100 and decimal 0.321000 e plus 2 both normalize to the equivalent value decimal 32.1. Note that rounding is applied before reducing to simplest form. In the latest versions of the specification, this operation is also known as reduce. Number underscore class context is equal to none. Return a string describing the class of the operand. The returned value is one of the following 10 strings: minus infinity, indicating that the operand is negative infinity; minus normal, indicating that the operand is a negative normal number; minus subnormal, indicating that the operand is negative and subnormal; minus 0, indicating that the operand is a negative 0; plus 0, indicating that the operand is a positive 0; plus subnormal, indicating that the operand is positive and subnormal; plus normal, indicating that the operand is a positive normal number; plus infinity, indicating that the operand is positive infinity; nan, indicating that the operand is a quiet nan, not a number; snan, indicating that the operand is a signaling nan. Quantize exp rounding is equal to none, context is equal to none. Return a value equal to the first operand after rounding and having the exponent of the second operand. Decimal 1.4 quantize decimal this print 1.414. Unlike other operations, if the length of the coefficient after the quantize operation would be greater than precision, then an invalid operation is signaled. This guarantees that unless there is an error condition, the quantized exponent is always equal to that of the right hand operand. Also, unlike other operations, quantize never signals underflow, even if the result is subnormal and inexact. If the exponent of the second operand is larger than that of the first, then rounding may be necessary. In this case, the rounding mode is determined by the rounding argument if given, else by the given context argument. If neither argument is given, the rounding mode of the current thread's context is used. An error is returned whenever the resulting exponent is greater than E max or less than E tiny. Radix return decimal 10, the radix base in which the decimal class does all its arithmetic, included for compatibility with the specification. Remainder underscore near other context is equal to none. Return the remainder from dividing self by other. This differs from self mode other in that sign of the remainder is chosen so as to minimize its absolute value. More precisely, the return value is self minus n into other, where n is the integer nearest to the exact value so of self by other. And if two integers are equally near, then the even one is chosen. If the result is 0, then its sign will be the sign of self. Decimal remainder near 10 minus 2. Minus 2. Decimal 25 remainder near 10 5. Decimal 35 remainder near 10 minus 2 minus 5. Rotate other context is equal to none. Return the result of rotating the digits of the first operand by an amount specified by the second operand. The second operand must be an integer in the range precision through precision. The absolute value of the second operand gives the number of places to rotate. If the second operand is positive, then rotation is to the left, otherwise rotation is to the right. The coefficient of the first operand is padded on the left with zeros to length precision if necessary. The sign and exponent of the first operand are unchanged. Same underscore quantum other context is equal to none. Test whether self and other have the same exponent or whether both are an. This operation is unaffected by context and is quiet. No flags are changed and no rounding is performed. As an exception, the C version may raise invalid operation if the second operand cannot be converted exactly. Scale B. Other context is equal to none. Return the first operand with exponent adjusted by the second. Equivalently, return the first operand multiplied by 10 power other. The second operand must be an integer. Shift other context is equal to none. Return the result of shifting the digits of the first operand by an amount specified by the second operand. The second operand must be an integer in the range minus precision through precision. The absolute value of the second operand gives the number of places to shift. If the second operand is positive, then the shift is to the left, otherwise the shift is to the right. Digits shifted into the coefficient are zeros. The sign and exponent of the first operand are unchanged. SQRT context. Return the square root of the argument to full precision. To underscore and underscore string context. Convert to a string using engineering notation if an exponent is needed. Engineering notation has an exponent which is a multiple of 3. This can leave up to 3 digits to the left of the decimal places and may require the addition of either 1 or 2 trailing zeros. For example, this converts decimal 123e plus 1 to decimal 1.23e plus 3. 2 underscore integral rounding is equal to none. Identical to 2 integral value method, the 2 underscore integral name has been kept for compatibility with older versions. 2 underscore integral underscore exact rounding is equal to none. Context is equal to none. Round to the nearest integer, signaling inexact or rounded as appropriate if rounding occurs. The rounding mode is determined by the rounding parameter if given, else by the given context. If neither parameter is given, then the rounding mode of the current context is used. 2 underscore integral underscore value rounding is equal to none. Context is equal to none. Round to the nearest integer without signaling inexact or rounded. If given, applies rounding, otherwise uses the rounding method in either the supplied context or the current context. Logical operands. The logical AND, logical invert, logical OR and logical XOR methods expect their arguments to be logical operands. A logical operand is a decimal instance whose exponent and sign are both 0 and whose digits are all either 0 or 1. Context objects. Contexts are environments for arithmetic operation. They govern precision, set rules for rounding, determine which signals are treated as exceptions, and limit the range of exponents. Each thread has its own current context which is accessed or changed using the getContext and setContext functions. Decimal.getContext return the current context for the active thread. Decimal.setContext C set the current context for the active thread to C. You can also use with statement and the local context function to temporarily change the active context. Decimal.local context ctx is equal to none ** keyword ars. Return a context manager that will set the current context for the active thread to a copy of ctx on entry to the with statement and restore the previous context when exiting with the with statement. If no context is specified, a copy of the current context is used. The kw argument is used to set the attributes of the new context. For example, the following code sets the current decimal precision to 42 places, performs a calculation, and then automatically restores the previous context. From decimal, import local context. With local context as ctx dot precision is equal to 42, s is equal to calculate something, s is equal to plus s, round the final result back to the default precision. Using keyword arguments, the code would be the following. From decimal, import local context. With local context, precision is 42, as ctx, s is equal to calculate something, s is equal to plus. Resist type error if KWR supplies an attribute that context doesn't support. Resist either type error or value error if KWR supplies an invalid value for an attribute. New context can also be created using the context constructor described below. In addition to the module provides three pre-made contexts. Class decimal.basic context. This is a standard context defined by the general decimal arithmetic specification. Precision is set to 9. Rounding is set to round half up. All flags are cleared. All traps are enabled. Treated as exceptions except inexact, rounded, and subnormal. Because many of the traps are enabled, this context is useful for debugging. Class decimal.extended context. This is a standard context defined by the general decimal arithmetic specification. Precision is set to 9. Rounding is set to round half even. All flags are cleared. No traps are enabled so that exceptions are not raised during computations. Because the traps are disabled, this context is useful for applications that prefer to have result value of NaN or infinity instead of raising exceptions. This allows an application to complete a run in the presence of conditions that would otherwise hold the program. Class decimal.default context. This context is used by the context constructor as a prototype for new context. Changing a field such as precision has the effect of changing the default for new context created by the context constructor. This context is most useful in multi-threaded environments. Changing one of the fields before threads are started has the effect of setting system-wide defaults. Changing the fields after threads have started is not recommended as it would require thread synchronization to prevent race conditions. In single threaded environments, it is preferable to not to use this context at all. Instead, simply create context explicitly as described below. The default values are context.prac28, context.rounding, round half even, and enable traps for overflow, invalid operation, and division by 0. In addition to the three supplied contexts, new context can be created with context constructor. Class decimal.context, prac is equal to none, rounding is equal to none, min is equal to none, mx is equal to none, capitals is equal to none, clamp is equal to none, flags is equal to none, traps is equal to none. Creates a new context. If a field is not specified or is none, the default values are copied from the default context. If the flags field is not specified or is none, all flags are cleared. Prac is an integer in the range 1 max prac that sets the precision for arithmetic operations in the context. The rounding option is one of the constants listed in the section rounding modes. The traps and flags fields list any signals to be set. Generally, new context should only set traps and leave the flags clear. The emin and emax fields are integers specifying the outer limits allowable for exponent. Emin must be in the range mean emin 0, emax in the range 0, max emax. The capitals field is either 0 or 1 the default. If set to 1, exponents are printed with capital E, otherwise a lowercase e is used. Decimal 6.02 E plus 23. The clamp field is either 0 the default or 1. If set to 1, the exponent E of a decimal instance representable in this context is strictly limited to the range E min minus prac plus 1 less than equal to E less than equal to E max minus prac plus 1. If clamp is 0, then a weaker condition holds. The adjusted component of the decimal instance is at most E max, but clamp is 1, a large normal number will where possible have its exponent reduced and a corresponding number of zeros added to its coefficient. In order to feed the exponent constants, This preserves the value of the number but loses information about significant trailing zeros. For example, context break is equal to 6, Emax is equal to 999, clamp is equal to 1. Dot create decimal 1.23 E999 prints decimal 1.23000 E plus 999. A clamp value of 1 allows compatibility with the fixed with decimal interchange formats specified in IEEE 754. The context class defines several general purpose methods as well as a large number of methods for doing arithmetic directly in a given context. In addition, for each of the decimal methods described above, with the exception of the adjusted and s-tuple methods, there is a corresponding context method. For example, for a context instance C and decimal instance x, c.exp x is equivalent to x.exp context is equal to c. Each context method accepts a Python integer, an instance of integer anywhere that a decimal instance is accepted. Clear flags, clear traps, copy decimal, create decimal. Return a copy of decimal instance. Create decimal creates a new decimal instance from num but using self as context. Unlike the decimal constructor, the context precision rounding method flags and traps are applied to the conversion. This is useful because constants are often given to any greater precision than it needed by the application. Another benefit is that rounding immediately eliminates unintended effects from the digits beyond the current precision. In the following example, using unrounded inputs means that adding 0 to a sum can change the result. Get context.track is equal to 3 decimal 3.4445 plus decimal 1.0023 decimal 4.45 decimal 3.445 plus decimal 0 plus decimal 1.0023. This method implements the two number operation of the IBM specification. If the argument is a string, no leading or trailing white space or underscores are permitted. Create decimal from float. Create a new decimal instance from a float f but rounding using self as context. Unlike decimal.fromFloat class method, the context precision rounding method flags and traps are applied to the conversion. Context is equal to context precision 5, rounding is equal to rounding down. Context.create decimal from float math.py decimal 3.1415. Context is equal to context preg 5, traps is equal to inexact. Context.create decimal from decimal. E-tiny returns a value equal to E mean minus preg plus 1, which is the minimum exponent value for subnormal results. When underflow occurs, the exponent is set to E-tiny. E-top returns a value equal to E max minus preg plus 1. The usual approach to working with decimals is to create decimal instances and then apply arithmetic operations which take place within the current context for the active thread. An alternative approach is to use context methods for calculating within a specific context. The methods are similar to those for decimal class and are only briefly recounted here. Abs returns the absolute value of x. Add xy return the sum of x and y. Canonical x return the sum decimal object digit. Compare compares x and y numerically. Compare signal xy compares the values of the two operands numerically. Compare total mag. Copy abs, copy negate, copy sign, divide integer dmod, exp, fma, is canonical, is finite. These are the same methods as explained above. Is nan, is normal, is qnan, is signed, is san, is subnormal, is 0, ln l, log 10, log b, logical and logical invert, logical or logical xor, max mag, mean max underscore mean underscore mag, minus multiply, next minus next plus next toward, normalized number class, plus power xy modulo is equal to none. Return x to the power of 5 reduced modulo is given. With two arguments, compute x power y. If x is negative, then y must be integral. The result will be inexact unless y is integral, and result is finite and can be expressed exactly in precision digits. The rounding mode of the context is used. Results are always correctly rounded in the Python version. decimal 0 or power decimal 0 results in invalid operation, and if invalid operation is not trapped, then result is decimal NaN. With three arguments, compute x power y modulo percent modulo. For the three argument, form the following restrictions of on the argument hold. All three arguments must be integral, y must be non-negative, at least one of x and y must be non-zero, modulo must be non-zero, and have at most precision digits. The value resulting from context dot power x y modulo is equal to the value that would be obtained by computing x power y percentage remainder modulo with unbounded precision, but is computed more efficiently. The exponent of the result is 0 regardless of the exponents x, y, and modulo. The result is always exact. Quantize x, y, radix, remainder x, y, remainder near x, y, rotate, same quantum, scale v, shift, sqrt, subtract, 2 engineering string, 2 integral exact, 2 science string. Constant. The constants in this section are only relevant to the C module. They are also included in the pure Python version of for compatibility. Decimal dot max prac, mean emax, mean underscore emean, mean underscore etiny, 32-bit, 64-bit. This one. Decimal dot have underscore threads. The value is true deprecated because Python now always has threads. Decimal dot have context var. The default value is true if the Python is configured using the without decimal context var option. The C version uses the thread local rather than a coroutine local context, and value is false. This is slightly faster in some nested context scenarios. Rounding modes. Decimal dot rounding ceiling, decimal dot rounding down, rounding floor, rounding half down, round half even, round half up, round up, round 0.5 up. Signals. Signals represent conditions that arise during computation. Each corresponds to one context flag and one context trap enabler. The context flag is set whenever the condition is encountered. After the computation, flags may be checked for informational purposes. For instance, to determine whether a computation was exact. After checking the flags, be sure to clear all flags before starting the next computation. If the context trap enabler is set for the signal, then the condition uses a Python exception to be raised. For example, if the division by 0 trap is set, then the division by 0 exception is raised upon encountering the condition. Class decimal dot clamped. Altered an exponent to fit representation constraint. Typically, clamping occurs when an exponent falls outside the context emean and emax limits. If possible, the exponent is reduced to fit by adding zeros to the coefficient. Class decimal dot decimal exception. Base class for other signals and subclass of arithmetic error. Class decimal dot division by 0 signals the division of a non-infinite number by 0. Can occur with division, modular division, or when raising a number to a negative power. If this signal is not trapped, return infinity or minus infinity with the sign determined by the inputs to the decimal dot inexact indicates that rounding occurred and the result is not exact. Signals when non-zero digits were discarded during rounding. The rounded result is returned. The signal flag or trap is used to detect when results are inexact. Class decimal dot invalid operation. An invalid operation was performed indicates that an operation was requested that does not make sense. If not trapped, returns an n. Possible causes include infinity minus infinity, 0 into infinity, infinity divided by infinity, x mod 0, infinity mod infinity mod x, sqrt minus x, and x greater than 0, 0 power 0, x power non-integer, x power infinity. Decimal dot overflow, numeric overflow, indicates the exponent is larger than context dot emax after rounding has occurred. If not trapped, the result depends on the rounding mode, either pulling inward to the largest representable finite number or rounding outward to infinity. In either case, inexact and rounded are also signaled. Decimal dot rounded. Rounding occurs though Possibly no information was lost. Signaled whenever rounding discards digits, even if those digits are 0, such as rounding 5.00 to 5.0, if not trapped, returns the result unchanged. This signal is used to detect loss of significant digits. Decimal dot subnormal exponent was lower than E mean prior to rounding. Occurs when an operation result in subnormal, the exponent is too small. If not trapped, returns the result unchanged. Decimal dot underflow. Numerical underflow with result rounded to 0 occurs when a subnormal result is pushed to 0 by rounding. Inexact and subnormal are also signaled. Decimal dot float operation enable stricter semantics for mixing floats and decimals. If the signal is not trapped default, mixing floats and decimals is permitted in the decimal constructor. Create decimal and all comparison operators. Both conversion and comparisons are exact. Any occurrence of a mixed operation is silently recorded by setting float operation in the context flags. Explicit conversions with a from float and create decimal from float do not set the flag. Otherwise, the signal is trapped. Only equality comparisons and explicit conversions are silent. All other mixed operations raise float operation. The following table summarizes the hierarchy of signals. Exceptions dot arithmetic error, exceptions dot exception, decimal exception, claimed division by 0, decimal exception, comma exceptions dot division by 0, inexact overflow, inexact rounded, underflow, inexact rounded, subnormal, invalid operation, rounded, subnormal, float operation, decimal exception, exceptions dot type error. Floating point knots. Mitigating round off error with increased precision. The use of decimal floating point eliminates decimal representation error, making it possible to represent 0.1 exactly. However, some operations can still incur round off error when non-zero digits exceed the fixed precision. The effects of round off error can be amplified by the addition or subtraction of nearly offsetting quantities, resulting in loss of significance. Nath provides two instructive examples where rounded floating point arithmetic with insufficient precision causes the breakdown of the associative and distributive properties of addition. Examples from semi-numerical algorithms, section 4.2.2. From decimal import decimal get context dot prac is equal to add UVW is equal to decimal comma decimal this comma decimal this u plus v plus w decimal 9.5 point this u plus v plus w decimal 10 u v w decimal this decimal minus 6 decimal 6 point something u into v plus u into w decimal this u into v plus w this. The decimal module makes it possible to restore the identities by expanding the precision sufficiently to avoid loss of significance. Get context dot prac is equal to 20 UVW, the same program now the results are identical. Special values. The number system for the decimal module provides special values including NaN, SNaN, minus infinity, positive infinity, and two zeros, plus 0 and minus 0. Infinites can be constructed directly with decimal infinity. Also, they can raise from dividing by 0 when division by 0 signal is not trapped. Likewise, when the overflow signal is not trapped, infinity can result from rounding beyond the limits of the largest representable number. The infinities are signaled and can be used in arithmetic operations where they get treated as very large indeterminate numbers. For instance, adding a constant to infinity gives another infinite result. Some operations are indeterminate and return an n, or if the invalid operation signal is trapped, raise an exception. For example, 0 by 0 returns an n, which means not a number. This variety of an n is quiet and once created will flow through other computations, always resulting in another n. This behavior can be useful for a series of computations that occasionally have missing inputs. It allows the calculation to proceed while flagging specific results as invalid. A variant is SNN, which signals rather than remaining quiet after every operation. This is a useful return value when an invalid result needs to interrupt a calculation for special handling. The behavior of Python's comparison operators can be little surprising where a NaN is involved. A test for equality where one of the operand is a quiet or signaling NaN always returns false even when doing decimal NaN is equal to decimal NaN, while a test for inequality always returns true. An attempt to compare two decimals using any of the less than equal to greater than equal to operators will raise the invalid operation signal if either operand is an NaN and return false if this signal is not read. Note that general decimal arithmetic specification does not specify the behavior of direct comparisons. These rules for comparisons involving an NaN were taken from the IEEE 854 standard. See table 3-4 section 5.7. To ensure strict standards compliance, use the compare and compare signal methods instead. The signed zeros can result from calculations that underflow. They keep the sign that would have resulted if the calculation had been carried out to greater precision. Since their magnitude is 0, both positive and negative zeros are treated as equal and their sign is informational. In addition to the two signed zeros, which are distinct yet equal, there are various representations of 0 with differing precisions yet equivalent in value. This takes a bit of getting used to for an eye accustomed to normalized floating point representation. It is not immediately obvious that the following calculation returns a value equal to 0. 1 by decimal infinity decimal 0e minus 100026. Working with threads. The getContext function accesses a different context object for each thread. Having separate threads context means that threads may make changes such as getContext.track is equal to 10 without interfering with other threads. Likewise, the setContext function automatically assigns its target to the current thread. If setContext has not been called before getContext, then getContext will automatically create a new context for use in the current thread. The new context is copied from a prototype context called default context. To control the defaults to that, each thread will use the same values throughout the application. Directly modify the default context object. This should be done before any threads are started so that there won't be a rest condition between threads calling getContext, for example. Set application wide defaults for all threads about the to be launched. Default context.track 12. Default context for rounding down. Default context.traps extended context.traps.copy. Default context.traps invalid operation is equal to 1. Set context default context. Afterwards, the threads can be started. T1.start, T2.start, T3.start. Recipes. Here are a few recipes that serve as utility functions and that demonstrate ways to work with decimal class. Diff money FMT value places is equal to current is equal to currency this separator this DP this and position is equal to blank negate is equal to minus tail negate. Convert decimal to a money formatted string. Places current sap DP. These are the examples. Cos, sine, decimal question. It is cumbersome to type decimal 1 2 3 4 5. Is there a way to minimize typing when using the interactive interpreter? Some users abbreviate the constructor to just a single letter. D is equal to decimal D. This. Question. In a fixed point application with two decimal places, some inputs have many places and need to be rounded. Others are not supposed to have excess digits and need to be validated. What method should be used? The quantize method rounds to a fixed number of decimal places. If the inexact trap is set, it is also useful for validation. Two places decimal 10 power minus 2, same as decimal this. Round to two places decimal 3.212, quantize two places this. Validate that a number does not exceed two places. Decimal 3.21 dot quantize two places. Context steps is equal to inexact. Once I have valid two place input, how do I maintain that invariant throughout an application? Some operations like addition, subtraction and multiplication by an integer will automatically preserve fixed point. Other operations like division and non-integer multiplication will change the number of decimal places and need to be followed up with the quantize step. A is equal to decimal this, b is equal to decimal this, a plus b is equal to this, a minus b is equal to this, a into this, a into b dot quantize two places this, and b by a quantize two places this. In developing fixed point applications, it is convenient to define functions to handle quantized step. Diff mul xy comma fp two places, return x into y dot quantize fp, edu fp, mul ab div ab. There are many ways to express the same value. The numbers 200, 200.02 e2 and 0.02 e plus 4 are all have the same value at various precision. Is there a way to transform them to a single recognizable canonical value? The normalized method maps all equivalent values to a single representative values. Map decimal to this dot split v dot normalize for v in values. Normalize. When does rounding occur in a computation? It occurs after the computation. The philosophy of the decimal specification is that numbers are considered exact and are created independent of the current context. They can even have greater precision than current context. Computation process with those exact input and then rounding or other context operations is applied to the result of the computation. Get context dot track 5 pi decimal this pi plus 0 this pi plus minus decimal this pi plus 0 minus this. Some decimal values always print this with exponential notation. Is there a way to get a non-exponential representation? For some values, exponential notation is the only way to express the number of significant places in the coefficient. For example, expressing 5.0 e plus 3 as 5000 keeps the value constant but cannot show the original's two place significance. So these are the questions. Here question answer. Here question answer. This one. Thank you.